Good morning, everybody. Let us start our discussion on the sampling methods for inference. So a quick recap, our goal was to draw and sample from an unknown distribution, or rather a complex distribution, often the posterior distribution that we are interested. So we are interested to draw a sample from theta, p theta given x. As it turns out that often if we express p theta given x in terms of the Bayes theorem, we know the denominator, but we don't know we know the numerator, we don't know the denominator, which is a constant, the normalizing constant. So we know the distribution only up to the normalizing constant. And using only this much information, we see that we can often draw samples from the posterior distribution. And these samples would help us in a method of approximate inferencing because of the Monte Carlo method, which the Monte Carlo method says is that if you have this is the statement, if you have a function fx and an unknown distribution px, expectation of fx with respect to px is approximated by 1 by m, where you draw m number of samples of the summation f of xi. So, so this is the theorem which says that this kind of sampling based inferencing will work if you have large number of samples. So this forms the basis of Monte Carlo approximation techniques. And one of the way that Monte Carlo is implemented is that you encapsulate an unknown distribution, a distribution, say p tilde z, with some constant times a standard or a known distribution. Then you follow a two-step process. First, you draw a sample from the known distribution, and then either reject or accept the sample. And in order to reject or accept the sample, you generate another random number, say an uniform random number between 0 and 1, and check whether that uniform random number between 0 and 1 is less than the ratio of the desired distribution to k times the constant times the known distribution. So it falls in the acceptance region or in the rejection region. You check so along this 0, 1 line where it falls. Okay, so it's not exactly the 0 and 1, the ratio is between 0 and 1. It's an upper bound, so it will be between 0 and 1. And we have seen that if we follow this method, then even though you reject maybe a large number of samples, the final samples that we get are a fair sample drawn from the complex distribution p tilde z. So this is what is called a Monte Carlo sampling or Monte Carlo approximation. We take help of another method, which is known as the Markov chain method. So a Markov chain consists of a set of states, and this set of states may be discrete or countable, maybe less in number, maybe large in number, whatever, and or also they may be continuous. So instead of just a discrete, finite number of states, the states can be anything on, say, R2 on the two-dimensional coordinate system. And you characterize a Markov chain by the transition probability from one state to another state. So I write it in this way, TL to R. So this is the probability from going from left to R. So the process is something like this. You start with an initial state, then again generate a random number. And note one thing, that if you add up all the outgoing probabilities for a particular state, they add up to 1. That's a requirement. Outgoing in the sense that it may come back to the same states. That also an outgoing, considered as an outgoing state. And the way the Markov chain progresses or simulates or executes is as follows. You start with an initial state, then generate a random number, and then depending on the value of the random number, you take one of the outgoing paths and move to another state. Okay, so it's probabilistic in the sense that you need a random number generator to decide to which state will go next, and you go on repeating this over several time steps. So if we trace the value of the state at every time step, you will get a sequence like this. This is for a two-state case. And not only that, you can actually think of as a at every step, if you ask the question that what is the probability that the system is in the Markov chain is in state say 1 or state L after the tth time step. So we write down this probability. So we see that in the initially it's in the left state, so probability of left is 1 and the right is 0. And then you can easily calculate what is the probability of being in L and R respectively in the next time step. How do we do? So for state 2, it's simple. With probability 0.3, it will still be in state L, and 0.7, it will be in state R. But let's look at x3. So that is interesting. The probability of it is in state L in x3 is defined by a marginalization process. Marginalization process like this, that you find out all the different ways you can be in state L. So you can from the previous state. So in the previous state, you can be in state L itself and come back to state L, which is given by, so probability of being in x3 being L, given x2 was also L, times probability in the previous state it was in L. And what is the probability of it being in L in or R in previous step is we have already calculated. We have already calculated in x2. So it's x2 equal to L times x3 to x2, where x2 is L. Similarly, it can be in previous step in R, and from R with 0.5 probability it can come to L. So it's from R to L, that probability will, that transition probability times the probability it's in R, which I have also calculated in the previous step. So if we plug in these values, you will get, so this can be thought of as a marginalization process, and you can keep on doing this at every step. What can be observed is that after large number of steps, these probabilities wouldn't change. It's for example, in this particular two-state Markov chain, these probabilities would be 0.42 for state L and 0.58 for state R. It's very easy to check that once you do this probability, and say it's for the x 1 million step, this is the probabilities you have got, and if you do it for x 1 million plus 1 and do this marginalization, you will, so it's 0.42 into 0.3 plus 0.58 into 0.5. That would be the next step. If you do this marginalization, you'll see that you will get back 0.42 again, and you will get back 0.58 again. So you get back the same number, same numbers, and this goes on forever, henceforth. So you can think of these two, in this case there are only two states, so these two probability values can be thought of as a distribution over these two steps. So the probability of being in L versus the probability being in R, they add up to 1. If we had more than two states, this would have been a 3-value distribution, still a discrete distribution, but a 3-value distribution. And if we had a continuous set of states, then this would be rather infinite number of possible values. So this would rather be a function, a distribution function, and that function itself would change with time, but eventually this would converge to a distribution. Okay, converge to a distribution of probability over the various states. In fact, there is a theorem that will happen. There is a theorem which says that this will always happen under certain condition. So now we want to use this kind of simulation, this kind of dynamics for generating samples. Okay, so as I have said that after large number of steps, this converges to a distribution, to a value of probability over the steps. So if you simulate this Markov chain for long enough, and then maybe throw away the first say 1,000 such states in this chain, 1,000 such samples in this chain, and look at the states of the chain thereafter, you'd as if get samples drawn from this two-dimensional distribution. If it is more than two-dimensional, that particular not two-dimensional, two-valued distribution. If you have more values from that discrete distribution, if you have continuous values, you have sort of drawn samples. You can think of these values of the states as samples drawn from a distribution over the different states. And if you look at the probabilities of the discrete case, you can easily do it. You just count how many are L, how many are R, and divide it by the total number of samples, you'll get a probability. If you look at the empirical value of probabilities, that means the frequency of these states in this chain, you will see that they will be pretty close to these convergent values, these converging probability values, or rather they will be close to the converging distribution. So in other words, if we throw away the first say 1,000 instances of this simulation, if you look at the Markov chain after a certain amount of time, the values of the states that we get, they are as if samples drawn from this converging distribution. So this is, for example, here this RRLL, this is a sample drawn from this 0.4 to 0.58 distribution. You see their proportional will be 2 by 5 and 3 by 5. Okay, so this gives us a way of sampling. So the process is like this. Suppose I have a target distribution Px from which I want to sample from. You just build a Markov chain whose converging probability is Px, whose converging probability is the distribution Px. And then start the Markov chain from any initial state, which again gives you a probability 1 for that state and 0 for the rest of the states. And then keep on simulating the Markov chain using the transition probabilities. If we do it for long enough, the states that you get in the chain would be samples drawn from Px. So the problem is that how do you know that this is this Markov chain that will converge to Px? So we have an inverse problem. We are given a Px, or we have some desired Px from which we want to draw samples from. We design a Markov chain, meaning we design transition probabilities and the states of a Markov chain such that the converging probability of the Markov chain is this desired Px. So it's an inverse problem. And once we do that, we can just simulate the Markov chain and come up with a sample of Px after throwing away some initial simulations. Okay, so now the question is, does a Markov chain always converge? Here is an example of the Markov chain which doesn't converge. It always oscillates. If you do it, however long you simulate it, you will see that it will be an oscillation between L and R and L and R. But there are most of the Markov chains do actually converge. We'll see when it is. But let us see what is the meaning of this converge. Meaning of the converge means Px is a converging distribution. We call it a stationary distribution of a Markov chain. The meaning of stationary, I think, is clear. It's a distribution Px is the stationary distribution of a Markov chain if this marginalization that we are doing in this step, remember we are doing in this step, this marginalization gives a value which is same as the left hand side. So it's the left hand side value is same as the value of the previous step. So if we start with Px and apply this marginalization, that means from state 1, from state x, how do you go to state x prime? Okay, so state x can take all sorts of possible values, any state. And so what is the probability you are in state x, and what is the probability you transition from state x to state x prime? You multiply these two. And then take another x. What is the probability? What is the probability? You add up all these things. So this is the total probability you can find in state x prime. If this probability in the previous step is same as the probability in the next step, so from x to x prime, if this probability doesn't change, that's what we have seen has happened here. Then we say this particular Px is invariant or stationary. Okay, and why it is stationary? Because once we anyway reach that distribution Px, we will forever stay at it. Okay, we will forever stay at it from henceforth. So that's a stationary distribution. If Px, so a Markov chain is characterized by the set of states and the set of transition probabilities. If Px, any Px which satisfies this value, this equation, it would be a stationary distribution by definition. And this should hold for all x actually. So for all x, this should hold. X and x prime. So there is a theorem which says that if the transition probabilities x to x prime for all x prime x are greater than 0, which means that you can reach any state from any other state, then there exists a unique stationary distribution for that particular Markov chain. So here it was not all non-zero, not all positive. So this doesn't have a stationary distribution, but this has a stationary distribution. Okay. In fact, it's easy to find the stationary distribution for a given Markov chain, at least for the discrete case. It's just the second eigenvector of the transition matrix, transition probability matrix. Note one thing, that I could have represented this Markov chain by a transition probability. So it's a 2 by 2 matrix, which says that probability of going from L to L and L to R and so on. Okay, another thing you notice that these transition probabilities, I can also write them as conditional probabilities. So given that you are in R, what is L? What is the probability you are in the next state you are in R? So I can always also write this as T of R given L. Okay, so any distribution with any Markov chain with positive transition matrices have an unique stationary distribution. Okay, and whatever initial state you start from, it will eventually, maybe it will take a long time, depends on where you have started from, you will end up in this stationary distribution. And such a process would be called an ergodic process. There is another way of looking at it. No. Okay. All right. So there is another way of looking at it. So you are looking at the, so let's say I have a continuous state space consisting of a, so every state is a point in two-dimensional space. You start from some initial state and then follow the transition matrix and move to a new state. So when you repeat this, and so you will get kind of a trajectory in the state space. You'll get a trajectory in the state space. And if we follow this trajectory for long enough, you will see that it kind of moves around in some part. It kinds of moves around in some part. Okay. moves around in certain part. And if we just look at points in this trajectory, they would as if be sorry, samples from some distribution, which is the stationary distribution. Let's say the stationary distribution is a mixture of two Gaussians. Okay, so a mixture of two Gaussians. So this would be the initial sort of burn-in region, which we can throw away. And if we look at rest of the sample, this would be a trajectory. This would be points on a trajectory. They would follow this distribution. And this region is called the burning region of the trajectory. And these regions are called the mixing regions of the trajectory. When it has converged, so this region is basically when I have converged to this distribution, the stationary distribution. Okay, so we also call the Markov process instead of transition to be mixed. So this is the mixing region and this is the burning region, or rather, this is the region where it has converged to the stationary distribution. Okay, so now there are two factors which says how good this and okay. So finally, is that if we just look at these points in the trajectory in the mixing region, they would give the sample from these px converging distributions, stationary distribution that we are looking for, that we are trying to generate. So now the goodness of this Markov chain is decided by two things: how long you have to wait to get this sample. So there are two factors. First factor is how long this burn-in region is. Ideally, this should be small, but this also depends on where you have started from in the initial condition. Second is how fast, so this is your target distribution. Let's say this is the support of your target distribution. So this trajectory, is it quickly filling up this target distribution? It is quickly becoming ergodic. Ergodic means fills up everything. Is it quickly becoming ergodic, or it's the trajectory is moving slowly over a small region, so slowly over a small region and very slowly expanding to cover everything? We don't want. We want fast exploration of this thing. Okay, we don't want a slow exploration which is doing. We want a fast exploration because we would quickly get the sample. So this is the exploration dynamics. Okay, thinking of the Markov chain as a trajectory. So we want our burn-in to be fast as well as exploration dynamics to be fast. One of the requirements for exploration dynamics to be fast is that if you can think of every transition in this Markov chain as a step you are taking in this trajectory. You are moving forward in this trajectory. So if the step is small, you kind of slowly explore. If the step is large, you kind of rapidly explore. But that's all fine in the mixing region, but taking a large step in the burn-in region might be problematic. So you take a large step here, you may go far away from your target distribution, then you have to come back to your target distribution. So you waste a lot of time in the burn-in region. So if you take small steps, you do slow exploration. If you take large steps, if you are not yet in the mixing region, you are for a longer time in the burn-in region. You wander around in the wrong way in the burn-in region. So there has to be this is a very trade-off problem between if you take between exploration and convergence. Okay, so what we'll see is that we'll see example of two ways of constructing given a target distribution. So my problem now henceforth is, given a target distribution px or a desired distribution px from which you want to sample from, design a Markov chain whose stationary distribution is this Px. Okay, and once you have done that, we can easily generate sample using that Markov chain. We see two techniques. One technique will just use this concept of Markov chain for sampling. The second technique will combine the previous rejection sampling Monte Carlo technique with the Markov chain concept. So what it will do is that it will start with a Markov chain. It will start with a Markov chain, look at the samples, and if the samples are not good, it will ditch that Markov chain. It will ditch that trajectory and take another trajectory. Okay, and then again do for some time. If that chain again is not good enough, either it's taking a time in the burn-in region or not exploring properly or exploring very slowly, because we want to avoid slow exploration, we want to avoid large burning. If it does any of this, again you reject it and choose a new Markov chain. From that point onwards, not historically, not back in time, but from that point onwards, taking that as your initial point of a new Markov chain, you start your another Markov chain. Okay, so this can be thought of as a rejection sampling, not over points, but over Markov chains. It's a rejection sampling over different possible Markov chains. So it's combination of Monte Carlo with Markov chain. It's called a Markov chain Monte Carlo. So you know every Markov chain will have a stationary distribution, but we don't know what Markov chain will give the stationary distribution. So you take a lot of Markov chains and do a sampling among them and combine them finally to get your target distribution. So first let us take only the Markov chain method. Then later we will consider the MCMC method. All right, so the first method is something known as Gibbs sampling. Gibbs sampling. So I want to draw a distribution, a sample X from a target distribution Px. So let's say this is my input space x1, x2, and as you know, I'll design a Markov chain. So I have to design some transition probabilities of moving around so that the final trajectory is a sample from some target distribution Px. So I have to design a Markov chain whose stationary probability is Px. So this X can be anything. This can be discrete, this can be continuous. All I have to do is to design some transition probabilities. Of moving along this path. I'll describe a scheme which is particularly suitable when this x1, x2, rather this Px is a high dimensional distribution. High dimensional distribution. Okay, and we'll assume that even though we could not find the normalizing constant Z because it is a high dimensional distribution, but if we look at one-dimensional marginals of this high dimensional distribution, or rather one-dimensional projections of this high dimensional distribution, then I can easily find this Z. So this has a unknown normalizing Z, but its 1D marginals would have known Z, that is, they are analytically computable, or they can be easily, just like we have seen a method of 1D encapsulation, they can be easily sampled from, or can be easily sampled from. And this is the assumption. If this is required for this Gibbs sampling, easily sampled. Okay, so the only reason we are unable to sample from it directly is that it's a high dimensional distribution, but it's one dimensional marginals. So if we have say x1 to xk dimensions, each of these px1 given the others, px2 given the others, they can be sampled from either because they are analytic or because they can be easily approximated using a rejection sampling technique. Okay, so now let us define this Markov chain transition for this high dimensional distribution. So you start with some initial x, high dimensional x. So let me denote this as a k-dimensional distribution. So your x is a k-dimensional vector. Let me start with some initial x naught, which is x1 naught, x2 naught, and so on, xk naught. Okay, and from that, now I'm defining the transition probabilities. Okay, so which means how do I generate x1 from x naught? How do I generate x2 from x naught, and so on? So let me denote this as x new, as then x1 new, x2 new, and so on, and just x for the old one. So the transition probability is this way. So this is my transition probability. So x new follows from rather x1 new is, let me like this. Suppose I want to generate x1 from x1. So this is this x1 vector. My transition probability T x1 given x0 will be how I generate x1 from x0. So what I do is that in order to generate x1, let me call it at x new, I do one dimension at a time. I generate x11 first, then x21, then xk1. In this way, one dimension at a time, I generate the new vector. So pictorially, if this is my x old, let's say I call this x old vector, what I'll do is that for the x new, first I'll generate the first coordinate, then the second coordinate, and this will be by x new. I'll first generate first coordinate, then second coordinate. If there are more coordinates, I'll one by one generate them. Okay, so one dimension at a time, I'll generate the new x new. So this is the formula. So the first coordinate of x new is a random number generated according to this distribution. What is this distribution? This distribution is P of x1 given all the other dimension values to be constant. What is this constant? When I am generating x1 from x0, this x0's x2 to xk I am fixing as the initial values that I have chosen. Okay, so these values are 0, 0, 0. These are fixed. And I vary only x1. And how I vary x1? I vary x1 by a probability distribution, which is the conditional distribution of x1 given x2, x3, xk fixed at x2, 0, x3, 0, xk 0. I'll soon explain with an example with xk 0. Okay, so this is how I vary x1 by this conditional distribution. Note that this is a one-dimensional distribution and easy to sample by our assumption. Okay, so I generate, so this is one-dimensional distribution. I draw a single point from this one-dimensional distribution, and that point gives me x new. So part of my transition from x old to x new is done. Only one part of my transition is done. Now I do the second part. Second part, what I do, in order to generate x2 new, I fix x3 to xk as my x0, the old value that I have chosen in the previous iteration. And the x1 that I have generated in this previous step, that I use as a constant. Note that this conditional part, the right part of these conditionals are constant. They are fixed. Okay, so x3 to xk are the initial values. X1 is this new value I have generated, and X2 is a variable that I generate according to this conditional distribution. And once I generate it, I generate another part of the new transition, which is X2 new. Now go to X3, XK new. So what I'll do in XK new is that X1 new, X2 new I have already generated. Let's say up to XK minus 1 new I have already generated. Okay, I'll use that as constants and generate XK, and I get XK new. So the combination of these K substeps would give me a new vector, and then and only then after this K substeps, this one transition would be over. This one transition would be over, and I have got a new point X1 new, X2 new, XK new. I have got a new point in the trajectory. Okay. So basically I have designed a transition manner. So I have defined a transition probability from one step to new step using this one dimension at a time conditional distributions. Okay. So now the question is, and note that this transition probabilities I have done in a very simple way. So the transition probabilities are just for every dimension. It is just the conditional probability of the target distribution, the conditional probability of the target distribution one dimension at a time, given the rest of the dimensions fixed at the previous state value. Right. So this way I have generated my transition matrix. Let me explain with an example. Let's say I want to sample from a bivariate distribution. So let me draw a bivariate distribution. I'm drawing the equal probability contours. This is my X1, this is my X2. Let's say I have started with the initial condition, say 1, 1. This is my 0th. So let me call it as X0. I've started from here. Okay, so what will be my transition matrix? First look at X1. So this is my target distribution P X1, X2. Okay, so what will be my transition probability for the new step? It will be P X1 given X2 equal to 1. P X1 given X2 equal to 1. So let us see what is P X1 given X2 equal to 1. X2 equal to 1 means let's say this is 1. So I am fixing X2 here. So if I draw more contours of this distribution and fix your X2 as 2, then I will get X1. So basically I am cutting this two-dimensional distribution along this X1 X2 equal to 1 plane. Okay, so I will get something like this, some one-dimensional distribution like this. Right. So generate X1 according to this one-dimensional distribution. Let's say I get a value. Let's say what? Say X1 equal to. Let's say I get X1 equal to 2 by drawing a sample from this one-dimensional distribution. All right. So now fix X1 equal to 2, and now you transition X2. How do you transition X2? Use this conditional P X2. Note that this P X1 given X2 equal to 1, if this total thing is a bivariate Gaussian, this will be a univariate Gaussian. That can be algebraically proved. So P X2, the second transition probability is P X2 given X1 equal to 2 now. Given X1 equal to 2. So fix your X1 to be 2. Fix your X1 to be 2. Cut this distribution. That is, take the one-dimensional conditional. You get a distribution along X2 something like this. Now draw X2 according to that. Let's say you get X2 equal to 4. So your new point is 2, 4. New point is 2, 4. So from here, let's say this is 1, 1. I have moved to 2, 4. Sorry, not this. I moved to 2, 4. Okay, and repeat this. And repeat this. Okay, so you move to another point. And then again repeat this. You move to another point, and so on. You keep on moving. And you will see that I'll prove soon that if I go on doing this long enough, then this trajectory, points along this trajectory that I generate will follow this bivariate Gaussian distribution. Will follow this bivariate Gaussian distribution. Okay, so now I have to prove that this transition probabilities that I have defined in terms of the one-dimensional conditionals using the rest of the dimensions fixed at the previous point in the state. Not exactly previous point, it's the points that are already sampled in the previous substep. So these transition probabilities give Px as a stationary distribution. I am proving it only for a three-dimensional distribution, discrete distribution. You can generalize it. It's easy to realize that it can be generalized to anything. Okay, so I have to prove that P is a stationary distribution of Tx. Let us consider a 3D state xyz, and I move to a new state x prime, y prime, z prime according to the probability T xyz to x prime, y prime, z prime. Okay, I actually will not write it this way. I'll write it this way: x prime, y prime, z prime given x, y, z. Okay, so these probabilities I'll write this way. Okay, so I have to show this is equal to this. Let us start with the right hand side. Let us start with this. So I have three dimensions. So I'll do a summation. If it is continuous, this summation would be an integration. No, this will not be an integration. This will be a summation if there are 3 dimensions. Would be by the definition Pxyz into transition from xyz to x prime, y prime, z prime. Now see, we have what is our transition for 3 dimensions? It would be x1 new, x2 new, x3 new. Okay, these 3 transitions. So your new is a collection of these 3 transitions, 1 dimension at a time. And since each transition is independent, the probability of x1 new, x2 new, x3 new from x1 old, x2 old, x3 old would be product of px1 given x2 old, px2 given x1 new, x3 old, xk old into px3 given. It would be product of these 3 probabilities because these 3 are independent. Okay, I'm doing them independently. I'm not tying them up. I'm doing them independently. Okay, so this is the product of, so for 3 dimensions, it is the total transition probability is the product of these 3 conditional 1-dimensional probabilities. So it is a product of x prime given y equal to y, z equal to z, y prime, note the rule of Gibbs sampling, y prime given x equal to x prime because x prime I have already generated, z equal to z. Probability z prime given x prime, y prime both I have already generated, so x prime, y prime. Okay, so this part is this T transition and this part is Pxyz. Now let us see. See, this is a summation over xyz. And so this thing, this z prime given x prime, y prime, I am shortcutting it by this terminology, z prime given x prime, y prime. This is independent of xyz, so I can bring it outside. And similarly, this term P, only this term is a summation over x, and these 2 term does not have x. X prime, x is x prime fixed constant. So I move the x part to over only this much, P of xyz, and the remaining part y is variable, z is variable. So I sum it over yz. I sum it up over yz. Okay. This you can verify the steps actually. So this is a now next step. Next step is this summation is nothing but marginalization over x. So I would basically get this to be, I'll basically get this to be p y z. It is a marginalization over x, and p in p y z with this, you get p x prime y z. So you multiply this by this, you get this term, and this term remains. This term remains, but this term is again independent of y, and only this term, this product of this and this, is dependent on y. So this summation y I can bring only to this. Oh, there will be a bracket here, and this z would be summed over everything, for this as well as this, and this is independent of that. Okay, so now you see this is again a marginalization over, this is again a marginalization over y, so only this part is p x prime z, and p x prime z, if we combine with this much, if you multiply this with this, you get p y prime x prime z, you get p y prime x prime z. So there is equal to here p y prime x prime z, and summation over z, and this part is still there, and this is again a marginalization over z, so I get this to be p y prime x prime, and this part is there, and if I combine these two, I get p x prime y prime z prime. So you see, so now finally this is equal to this, what we started with. So this is precisely what we are trying to prove. This is precisely what we are trying to prove. So x prime is 3 dimensions, x prime, y prime, z prime, and x is 3 whole dimensions, x, y, z, and t is what we have explained. So this is equal to this. So basically this Gibbs sampling transition gives your p as a target or a desired distribution. This is the stationary distribution of t. So this completes the proof of correctness of Gibbs sampling. And this is how it would actually proceed. Gibbs was actually a chemist. He was considered the father of physical, one of the earliest American-born scientists. Okay, so as a summary, we see that what happens is that it has some disadvantages. First thing is that it has a long burn-in phase. It takes a lot of time because every step that we are taking is actually small. If we look at these probabilities for most of the distributions, these steps would be very small. So the next sample would be very much, next step would be very much correlated with the previous step. So not only the burn-in is long, your exploration is also very slow. You move around in a small part a lot. So you have very correlated or small steps. Second is that you need if you have a really large dimension, you need a lot of steps. This we'll see is a problem because let's say you do a text analytics where you have a distribution over all words and you really have large number of words. This takes many sub-steps. Second is you cannot parallelize the sub-steps because you see, until and unless you have generated x1 new, you cannot generate x2 new. Until and unless you have generated both x1 and x2 new, you cannot generate x3 new. So you cannot parallelize, you have to do them sequentially. You cannot accelerate by using parallel computing. So these are the problems. The main problem, it has long burn-in phase and and also exploration is very slow. But it is a very simple method in the sense that it is hyperparameter free. The transition matrix is directly defined in terms of the target distribution. It's hyperparameter free, and there is no optimization or anything, and it is unbiased in the sense that if you simulate this Gibbs sampling long enough, you eventually always get the target distribution, sample drawn according to a target distribution. You may have to wait for long, but you will eventually get. So your error will eventually go to 0. So this is an unbiased sample in the long run, but the long run is often a really long run. So that's an disadvantage. There are many variations to this. One is called a collapsed Gibbs sampling. So that means you see that these dimensions I'm talking of in Gibbs sampling, this will actually be the, you remember originally you are trying to estimate P theta given X. So this would be X1, X2 would really be theta 1, theta 2, theta K. So these are the different parameters. Let's say all the weights of a neural network or all the mean and variances of a large dimensional Gaussian. So this would be the parameters. Often it may be the case that some of these parameters value I know, maybe from side knowledge or something, I know some of the parameter values. So I can drop those particular steps from these sub-steps. So instead of x1 new, x2 new, for the particular x, say xi and xj, which I know already, I have already estimated, I need not re-estimate them, I already know what they are, I may drop those steps, drop those updates, because they are known, and use their value in all these calculations, fixed value in all these calculations. So if that be so, it's called a collapsed Gibbs sampling. And this process of dropping some of the parameters is called a Rao-Blackwellization process. Rao-Blackwellization process. And it can be, there is a theorem which shows that it always underestimates the variance if we do it this way. Okay, so some z we know and theta you want to find out, or maybe theta is dependent on some of the z's. Z is a kind of latent variable. Then you can simplify your collapse Gibbs sampling to reduce the dimensionality somewhat. Often it turns out that if we have many parameters, only few of the parameters are unknown, just unknown. So Rao-Blackwellization indeed is very useful. Okay, so now we try to remove this drawback of Gibbs sampling, that steps are small. We want to take larger steps, but we want to reduce burn-in time also. So that would be the next algorithm we study, something called a Metropolis-Hastings sampling, which is really a Markov chain Monte Carlo method, which combines Markov chain with Monte Carlo. I'll take a small break. I'll come back at 9:05. We come back at 9:05.
Excuse me, sir.
Yeah, please.
Sir, I have a doubt. Can I ask?